Okay, so in this presentation I'm going to outline how we can create authenticated encryption using the ElGamal public key encryption method and also the cryptology library. Okay, so public key encryption normally involves three different methods. So with public key encryption we have a private key, that's a secret key, and we also have a public key. So if Bob wants to send Alice some encrypted data, what you can do is send her public key over. Bob can then encrypt with that public key, and then hopefully we'll use the private key to be able to decrypt it from Alice's side. But there's a slight problem with this, and the problem is that it's not so easy to encrypt a lot of data. So we often use what's called a hybrid method of encrypting data with public key encryption. And a typical method is to take Alice's public key, take the encryption key that Bob wants to use, and then to encrypt the encryption key, the symmetric key encryption key, with Alice's public key, and then send over the encrypted data for Alice to be able to reveal the key with her private key. But we'll see there is a method that can be used in ElGamal that allows us to be able to use both symmetric key encryption for the encryption and public key encryption for the key generation. So with RSA we create two prime numbers, and then we create a modulus p times q, and then from there we work out, or we have a value of e, and we can then find the value of d, which is the decryption value. When we're encrypting, we take the message to the power of e, and then we take mod of n. That equals our cipher. Then to decrypt, we take the cipher to the power of d, and then take mod n again, and we should get our original message back again. The way that this d value is calculated is that we take a value of phi, which is equal to p minus 1 times q minus 1. And then we find the inverse of the e value that we select, mod of phi. And that gives us our public key, which is e comma n, and our private key, which is d comma n. The problem with RSA is that we now need very large prime numbers, typically 1000 bit prime numbers, to make a modulus of 2000 bits and so on. So the computation becomes extremely difficult now. The method we often use now is elliptic curve in cryptography. With elliptic curve cryptography, we have a curve. Let's say we have a curve that looks like this: ax plus b mod of p. Okay, and when we plot that, we get a standard looking elliptic curve. When it brings in the mod p, we have what's called a finite field. This is typically a 256-bit prime number, so you can see it's a lot smaller than with RSA. But basically what we do is that we have a value of g, which is the base point. We have a secret value, let's call it s, which is a scalar value, and then we multiply that, or we add g s times. That's g plus g plus g plus g s times to give us a public key point. It is not possible to discover the value of s even though we have the base point g and we have the public key value. And this is a very efficient method. It's very fast and very efficient in terms of the sizes of the numbers that we're doing. 256 bits is the maximum size of the values that we need to work with. So elliptic curves are a very good method and are used in elliptic curve Diffie-Hellman and elliptic curve DSA, digital signature algorithm for signatures. So for key exchange, elliptic curve Diffie-Hellman, and for digital signatures, ECDSA. We now see other methods called EdDSA, which uses another type of curve called curve 25519, and this is an Edwards curve, and often we can use this in terms of using the ED 25519 curve. If you're interested, it gets its name from the prime number, which is 2 to the power of 255 minus 19. So that's a very efficient method, but there are some advantages in the method that we'll be looking at. So the third method that we have is with discrete logarithms. And discrete logarithms allow us to have a base value, g is called the generator value, and we raise to the power of x, and we take mod of a prime number. And if we make p large enough, it's actually very difficult to discover the value of x from there. So this is the discrete log problem. It's a hard problem if we make p larger than 1000 bits or more. It's actually really difficult to discover that. And because we're using the mod p operation, we can still do operations as we would, but we constrain them within a finite field. So when we raise this to the power of y, then that is the same as g to the power of x, y mod p. So all of our normal operations that we would do, we can still do them, but we do them within a finite field using this mod p. It constrains the sizes of the numbers that we have, but still keeps the maths of it correct. So that's an interesting area, and if we do g to the power of x, g to the power of y, mod p, that is the same as g to the power of x plus y mod p. But the problem with discrete logs has been that we need ever-increasing large sizes for the prime number to keep it secure. So we would often use this in terms of the Diffie-Hellman method and key exchange. But in public key encryption, we can use the ElGamal method, and we'll just outline that in a little minute. The other thing that is very useful is that, let's say that Bob has a symmetric key and then encrypts some data in there. So he can send that to Alice, but let's say Eve copies it and then sends it back in there. And that's possible because the same cipher stream will work again. So we need to protect against playback. So one of the methods that we use is to add some additional data into the encryption process that isn't part of the key, but is data that will bind it to a certain session or a certain encryption, a certain encryption process. It could be the port number, it could be the session ID, it could be something else. We add that into the mix. So when at the other end, Alice looks at the additional data, when she's decrypting it, she will authenticate the encryption process with this additional data. If it doesn't match up, she won't be able to decrypt the data. So we see this increasingly within symmetric key encryption, where we have authenticated encryption with additional data. And one of the most popular methods to do this is with GCM. GCM mode of AES is actually a stream encryption mode, Most people think of AES as a block cipher method with CBC and ECB and so on, but we can convert it into stream cipher mode, which makes it very efficient, and we don't have padding and blocks and so on. It also makes it extremely fast compared with block modes. So the method that we're going to integrate, we'll try to integrate this AEAD into the ElGamal encryption. Okay, so I'll give you some background on ElGamal and how it actually works. Okay, this is the discrete log method. We start off with a base generator. Then, in this case, Bob generates a random value up to the value of p minus 1, and then takes mod of p. Mod, as hopefully you'll know, is the remainder after an integer division. So this becomes Bob's public key, and his private key is x. Now, if Alice wants to send Bob some data, she generates a new random number for this encryption and takes g to the power of that k mod p. And then she also creates another value, which is Bob's public key to the power of k, and then multiplies it by the message converted into an integer value, and then takes the mod of p. At the other end, Bob recovers the message by taking the b value, and then taking the a value, raising it to the power of x, and dividing it, and then take mod p. So the thing that you may question here is, how do we divide within modular forms? And there's a proof there that it all works and that we should cancel out in the end. That becomes that, so on, and we end up with the message to make it work. So this was the method that was proposed for ElGamal, but it's hardly ever used these days because elliptic curve cryptography has taken off, and now we don't really use these discrete log methods anymore. We use the efficient methods of elliptic curve. So here we can end up with 1k, 2k, even 4k key sizes for the value of p. In elliptic curve, we only have maybe about 256 bits to have the same level of security. Okay, so here's a Golang program which does this. From here we're using big integers because in this case we will have integer values that might have thousands of bits in them. So we can see here this is us generating the value g to the power of x mod p, gives us our exponent, and there's the private key, and there is the public key for Bob. So there's some of the sizes that we would have. You can see as we get bigger sizes, their big integers become quite large. Now we can have g to the power of k. G is the base generator. Typically g is 2 or 3. Sometimes it can be 5. Okay, it's quite a small value, but it doesn't take much for it to become the result to become very large. Okay, so we have k here, which is the random number that Alice is going to generate. Then we'll do that with mod p for that. Next, we'll raise the public key to the power of k, and then multiply by the message here. And then eventually we should get to the result. We do a modular inverse. To get the inverse, we do a modular inverse of a to the power of x to give us this value here, and then we basically just multiply it together to give the value. Okay, so it's not really a divide, it's a modular inverse to get the a to the power of x. Then after that, we should have our message back, we convert it to bytes, and we're okay. So that's the standard form that we would have for our ElGamal. There's some of the values here, 42, there's the message, and so on. Here are the values for the public key. There's the value we generate, and so on. There's the two elements of the cipher then. So let's look at converting this into elliptic curve. The way that we do that is we take g to the power of x mod p. So anything in this form can be converted into an elliptic curve form by multiplying rather than taking to the power of. So this form becomes this form. It's also a mod p, but this time it's the elliptic curve form. This is the base point rather than the generator value, and this is a scalar value. This is scalar, and this generates a point on the elliptic curve. Okay, so whenever we have an exponent, we can create a multiplication. And then whenever we have a multiplication, such as when we have a multiplication, we can have our point value. If we have g to the power of x and g to the power of y, that can become xg plus yg. So the multiplication becomes a point addition here. So when I'm multiplying two values together, it becomes an addition of 2 points on the elliptic curve. And it's quite easy to add points on the elliptic curve. It's quite easy to double them and so on. Okay, so whenever we're converting from g to the power of that and g to the power of z to the power of a and so on, whenever we have an exponent, we will drop that into a multiplication. And we have a multiplication here, then that would be z to the g, and then we have a exponent, so that becomes a there. Okay, so that's how we convert from a discrete log problem into an elliptic curve problem. So let's look at how we can encrypt, and I'm going to use the cryptology library here to be able to do this. So here's the code over here, and here is the method. So we'll just follow the method from here. Initially, Alice creates her private key, then generates our public key point. So that's the point on the elliptic curve here, xg. Okay, it's an elliptic curve point, so it has an x and a y, but we're using curve 25519, where we only use one of the coordinate values. So if we used other curves, such as P5256 and so on, or SEPT 256K1, we would have a public key value, which is an xy point. So if it was 256 bits for our private key, we'd end up with 512 bits for the public key. But in this case, we're using curve 25519, so we only have one of the points on the for the elliptic curve. Okay, so and curve 25519 is a very, very efficient curve. So we match the x value as a scalar onto the public key value to give us our point on the curve. In this case, it's ed 25519. And that becomes the public key for Alice. She sends that over to Bob. Bob will generate a new random number. We'll calculate C1, which is R times C1. So if we look over here, there we go. Okay, so in this case, here is the private key, scalar value. We then take the base generator value, the G value, and multiply it by X to give y is equal to xg here. Now we take C1, and C1 is equal to R times G. I say times, but it's G, the G point added R times. Now we take the message and we match the message onto the elliptic curve. So we find a point for the message when we hash it. This will allow us to be able to check the hash of the message later. Then we take C2, and C2 is equal to the random value times the public key of Alice plus this new hash method that we've hash value that we've hashed the message to. Okay, so then we go into a really interesting phase. So the phase that we go into now is to be able to create an encryption key with authenticated encryption. So we calculate the key by taking R, which is the new random number purely for this session, and multiply that by Y. So this becomes RY, becomes the encryption key. We'll create the key here that we've got, and then we'll create a GCM cipher for it. And then we take the additional data. In this case, we'll take the C1 value and we'll append it on with the C2 value. So it takes all the bytes from C1 and then adds on all the bytes from C2, and that becomes our additional data. We'll create a nonce value, random, for the AES encryption. The nonce value will be stored with the cipher, and then we'll encrypt. In this case, we're encrypting with the additional data, with the data from the message, the nonce and the nonce value. So that will now create our authenticated encryption. So on the other side, Alice receives the encrypted data, C1 and C2, and the nonce value that's been used for the encryption. She then takes her own private key and will regenerate the value of T by taking X, our private key, times C1. So we can see that hopefully here. Okay, so T is equal to X C1, and we'll just prove that's X and C1 is RG, which becomes RXG, which is equal to R times the public key. So that's the same as the key that Bob used there. So now Bob and Alice have the same symmetric key that's been used on either side. Now we need to generate the additional data. So from that we take C1 and C2 and append it on as before, and then we can then take the encrypted data, the additional data that we're taking. So you can see there's the append operation for C1 and C2, which has been received from Bob. We can then use the nonce from the encryption stream, and hopefully everything will work out and it will get our message back in the end. Okay, so I can show you the code running hopefully here. So hopefully I can show you the code running here. So here it is in there. So we can see here the basic method that we have. So let me just run that. Okay, so normally we would build it and then run. So I'll add a message of hello 123. Just give me a second. That should be main.go. And there is the data there. Okay, private key, public key, C1, C2, hash to the point, AAD. There's a nonce value, there's encrypted value that's gets sent from Bob to Alice, and we can see here that Alice has managed to decrypt that back into there. The two I find compressed is a way that we can actually have a shareable point on the elliptic curve. The way it's stored in the program isn't quite the same. This will allow us to be able to export the point. Because C1 is a point, C2 is a point, M is a point, Y is a point, and so on. only if it's not scalars can we actually just show the value. Okay, so that hopefully shows that, and there's a sample run there to show that it all works. From there, message, public and private key, C1, C2, hash to the point. There's the additional data, taking the appended value of C1 and C2 to create the additional data. There's the nonce, which is used in the encryption process, encrypted value, and then we end up with a decrypted value. Okay, so hopefully that's outlined how we can use ElGamal with elliptic curves and create efficient encryption. Thanks.